Welcome back, everyone. Ready for another deep dive into the OEIS?
Always.
Well, today we're looking at sequence A000152. Definitely a fascinating one, especially for those of you who love number theory.
For sure. It's all about the number of ways to represent an integer as the sum of 16 squares.
16 squares, huh?
Yeah.
16.
We've got the OEIS entry right here, of course.
Of course.
But we'll also be taking a look at the Wikipedia article on sums of squares, just to kind of get a wider view. Yeah.
You know, what I find really interesting here is how this sequence pushes beyond those classic theorems, the ones about sums of 3 squares or 4 squares.
Like Lagrange's and Legendre's theorems.
Exactly. It's like we're venturing into a less explored area of number theory, which is always exciting, right?
Okay, so A000152, just to be clear, it lists the number of ways we can write each integer starting with 0 as the sum of 16 squares.
16 squares, yeah.
And the first few terms, just to give everyone a taste, are 1, 32, 480, 4480, and 29152. Anything jump out at you just from looking at those numbers? Well, they're increasing pretty rapidly.
Yeah.
Which kind of suggests that as you go to larger numbers, there are many more ways to express them as sums of 16 squares.
So more ways to break them down, essentially.
Exactly. And the question then becomes, how much more?
That's a question.
And I think that's where the tools provided in the OEIS entry come in handy. We can start digging a little deeper.
Now you're talking. Okay, so one of the first things we see in the entry is the generating function. I have to admit, generating functions, they always seem a bit mysterious to me. Like, what exactly are they doing?
Oh, they're really cool once you get the hang of them. Think of a generating function as a way to pack all the information about a sequence into a single function. It's like a mathematical code, in a way.
A code?
Yeah. And for this sequence, A000152, the generating function is theta3, 0q16, theta3 being, of course, the third Jacobi theta function.
Right, the Jacobi theta function. I know they're important in number theory, but why does it matter that they show up here?
Well, Jacobi theta functions, they're kind of like celebrities in the world of math. They pop up in all sorts of unexpected places.
Like a mathematical Waldo.
Haha, yeah, kind of. And their appearance here in this generating function suggests that our sequence has some deep connections to other areas of math, like elliptic functions, modular forms, things like that.
So it's not just a random sequence. It's telling us something bigger about the structure of numbers.
Exactly. There's a hidden structure beneath the surface.
I love that. Okay, so we've got this generating function, this code that describes the sequence. But what about the actual nuts and bolts of how the sequence is generated?
Well, for that, we have the recursive formula.
Oh boy, recursive formulas.
I know they can look a little intimidating at first, but they're really quite elegant.
Okay, humor me. What's the formula for this one?
For A000152, it's AN32N times the sum from K1 to N of A1866690K times ANK with A01N.
Oh yeah, I'm lost already. What's A1866690?
So A1866690 is another sequence in the OEIS. It's closely related to our sequence.
Oh, okay.
And essentially what this formula is saying is that to calculate any term in the sequence, we need to know the previous terms.
So it builds on itself.
Exactly. It's a step-by-step process.
It's like a domino effect, kind of.
Exactly. You knock over the first domino, and it sets off a chain reaction that determines all the following ones.
And to make things even easier, the OEIS entry provides some Maple and Mathematica code. So you can actually put this recursive formula into action, see how it works.
Which is amazing. It's like having a powerful calculator that can handle all these complex calculations for us.
Computers, they're pretty handy sometimes.
For sure. But, sometimes it's good to step back from all the formulas and the code. Look at the bigger picture,
Absolutely. Get some perspective.
Right.
And the Wikipedia article on sums of squares is a perfect place for that. Speaking of which, I remember learning about Lagrange's 4-square theorem and Legendre's 3-square theorem back in my number theory class. Do those come into play here at all?
Oh, absolutely. They're foundational to understanding sums of squares in general. Lagrange's theorem, remember, it says that every natural number can be expressed as the sum of 4 squares.
Right, 4 squares.
And Legendre's theorem, it tells us that a number can be represented as the sum of 3 squares, only if it doesn't have a specific form.
Right, there are some exceptions. But those theorems, they deal with 3 or 4 squares. And our sequence, A000152, it's all about 16 squares. Is that difference significant?
Oh, it definitely is. Those classic theorems, they give us a solid foundation. But as we increase the number of squares, the patterns can change in some pretty surprising ways. It's like we're going from a 2-dimensional map to a 3-dimensional one. or even higher.
So we're venturing into uncharted territory.
Exactly. And that's what makes A000152 so intriguing. It raises all sorts of new questions.
Like, what are the rules in this new territory?
Right. What are the underlying patterns? How fast did these numbers grow? And how do they connect to other areas of mathematics?
So many questions. It seems like there's a lot more to discover about sums of squares than we might initially think.
Oh, absolutely. We've only just begun to scratch the surface.
I love it. More to come then.
Definitely more to come.
Okay, so we've covered a lot of ground already. Generating functions, recursive formulas. But can we maybe, zoom in a bit? Get back to the basics of A000152.
Back to the basics, sure.
Yeah, what do those first few terms in the sequence actually tell us? About sums of 16 squares, I mean.
Right, let's break it down. So the first term, it's 1.
1,
which corresponds to n equals 0. And basically it's saying there's only one way to represent 0 as the sum of 16 squares.
Which is it?
Using all zeros, of course.
Oh, right. 0 squared is still 0, so 16 of them added together is still 0. Makes sense.
Makes sense.
Okay, what about the next term?
So the second term is 32.
32, okay.
And that corresponds to n equals 1.
Okay.
So it's telling us there are 32 ways to express the number 1 as the sum of 16 squares.
Wait, 32 ways? How is that even possible? We're just talking about the number 1.
Well, remember, we're working with integers here.
Integers.
So that includes negative numbers as well.
Oh, okay.
So one way to get 1 is to have one of the squares be 1 and the rest be 0. But we could also have one square be negative 1 squared, which is also 1, with the rest being zeros.
I see. So we have different combinations of 1s, negative 1s, and zeros, all adding up to 1. That's pretty neat.
Exactly. And as n gets larger, the number of integers we can use increases.
Right. More options.
Which leads to a huge increase in the number of possible combinations. That's why the terms of A000152, they grow so quickly.
It's like the bigger the number, the more ways there are to build it with those 16 squares.
Precisely. So those numbers in the sequence, they're giving us a real concrete count of the possible ways to create these sums of 16 squares.
I'm starting to get it now.
Yeah.
But I imagine things get pretty complex when we start dealing with larger and larger values of n.
Oh, definitely. The number of combinations explodes. And that's where those computational tools we talked about earlier, they become absolutely essential. They can handle those huge numbers of calculations.
Thank goodness for computers.
Right. It would be pretty much impossible to do all those calculations by hand.
Yeah, I think my brain would melt. But it's amazing how technology lets us push the boundaries of what we can explore in math, you know?
It really is. It's like we're partnering with computers to uncover these intricate patterns.
Teamwork makes the dream work, as they say.
Ah, exactly. But speaking of pushing boundaries, remember that A000152 is all about sums of 16 squares.
16, right.
Which is a big leap from those classic theorems we talked about, the ones that deal with only 3 or 4 squared.
Yeah, a much bigger puzzle, it seems.
It is. And what's fascinating is that this exploration into higher numbers of squares reveals even more intricate behavior. It raises a whole new set of questions.
Like, what are the rules of the game when we're dealing with so many more squares?
Exactly. For instance, there's a lot of research going on about the distribution of these numbers, how fast they grow, how they connect to other areas of math.
It's like we're venturing into uncharted territory again.
We are, and that's what makes this sequence so exciting. It's a window into a less explored area of number theory.
I love that. Okay, so we've got the sequence itself, but the OEIS entry also has links to all sorts of research papers, right? Like congruences for sums of squares functions, things like that.
Yes. They might sound a little intimidating, but they really dive into the intricacies of A000152.
Seems like this one sequence has sparked a lot of research.
Oh, it has. They touch on some really advanced concepts, combinatorics, representation theory, even some pretty heavy-duty number theory.
Wow, that's impressive. It really shows that even though we're focusing on one specific sequence, it's connected to so many other ideas in math.
That's the power of the OEIS, really. It lets us see those connections, those hidden relationships that might have otherwise gone unnoticed. Each sequence is like a piece of a giant puzzle. And as we fit more pieces together, we start to get a clearer picture of the whole mathematical landscape.
That's a great way to put it. It makes me want to keep digging into the OEIS and see what other connections we can find.
Me too. There's always something new to discover. That's what keeps math so fascinating, don't you think?
Absolutely. It's like an endless adventure. You know, it's amazing to think that something as simple as adding squares can lead us to such a deep rabbit hole of math. It really makes you wonder what other treasures are hidden within those basic operations we take for granted.
Oh, absolutely. There are countless mathematical mysteries still waiting to be solved. But for now, maybe we can try to sum up what we've learned about A000152. See if we can bring it all together.
Yeah, that's a good idea. We've talked about the sequence itself, the generating function, the recursive formula, those classic theorems. Where do we even begin?
Well, I think one of the key takeaways here is that A000152 gives us a precise way to count how many ways we can represent integers as the sum of 16 squares. It's like a lens that lets us see those representations clearly.
And it takes us way beyond those familiar theorems, right?
Yeah.
Lagrange, Legendre.
Yeah.
Those guys were working with 3 or 4 squares. We're playing in a whole different league here.
Exactly, 16 squares. And along the way, we've encountered some pretty powerful tools, too. Generating functions, recursive formulas. I mean, they're a little mind-bending at first, but they really help us unlock the secrets of this sequence.
They do. And the connections to other areas of math, like those elliptic functions and modular forms, it just shows how interconnected everything is. Like we tug on one thread, and it unravels a whole tapestry of mathematical concepts.
I love that analogy. And it's true. A single sequence like 0000152 can act as a bridge between so many different ideas. It's a gateway to a whole new world.
And speaking of gateways, the OEIS entry itself is just the starting point, right? There are links to related sequences, research papers, tables with even more terms. It's like a treasure map for mathematicians.
It is an invitation to keep exploring. And who knows, maybe in the process of digging deeper, we'll uncover some new connections, some new insights that have implications beyond this one sequence.
That's the beauty of math, right?
Yeah.
There's always more to learn, always another layer to uncover.
Always. And speaking of uncovering layers, I do have one final thought for our listeners to ponder.
Oh, do tell. I love a good brain teaser.
Remember how we talked about Lagrange's four-square theorem?
Mm.
And how it can be visualized geometrically in 2 dimensions?
The squares fitting together.
Right. Well, I wonder if there's a way to visualize the representation of a number as the sum of 16 squares, maybe in a higher dimensional space. What would that even look like?
Ooh, that's a good one. It really challenges us to think outside the box, to consider the geometric implications of these number theory concepts. It makes you realize just how much there still is to explore in math.
It does. So to all our listeners out there, keep exploring, keep questioning, and keep pushing the boundaries of what we know about math. The adventure never ends.
Couldn't have said it better myself. Thank you all for joining us on this deep dive into OEIS sequence A000152. We hope you've enjoyed the journey as much as we have. Until next time, keep those mathematical minds sharp and stay curious.